pleasant break, and let's resume with Guillaume Quintin, who will be talking to us about ARM, basically the ACLE extensions. So, well, for a high order finite element kernel. So, Guillaume, you can introduce yourself and go ahead.
Okay. Hi everyone. So my name is Guillaume Quintin, obviously, and so I'm CEO of a small French company. In the south of Paris. So we are specialized in code profiling, code optimization on various hardware. You know, we do CPUs, GPUs, and other weird environments. I'm here to talk to you about the use of SVE intrinsics for optimizing a kernel, a computation kernel. So this is a joint work with Sylvain Juberty from Orléans University and Fabrice Dupro from ARM. So let's go. The kernel I will talk about is somehow similar to SpecFEM 3D. So it's a ground motion simulation based on the spectral finite elements methods. We have, unfortunately, an unstructured mesh. This means that we will have to do gathers and scatters, and so this is not that good for memory accesses. We have written the kernel with C intrinsics. So it's written C++ because it's a CPP file, but it's not really C++. It's more C than C++. But anyway, so the code is from is called FESpec, and it's developed at the BRGM. That's a French geological survey. Excuse me. So the original code was written in Fortran and uses MPI, of course. So we have a good internal scaling. So, for example, on the cochain 2, but a lot of engineers looked at the code and wanted, all the compilers to produce good, let's say, good assembly with a lot of vectorization. But even with pragmas and other stuff, the compilers usually don't auto-vectorize, or very bad. So I'm talking about every compiler that we could test, including ICC, GCC, Clang, ARM Clang, and other compilers. So basically, the kernel works on elements, and so for each element, so we have 5 by 5 by 5 points to treat. So what the kernel does is, so there's 3 steps basically. The first is the gathering step. So we collect points from memory. Then we compute internal forces, and then we update. We put results back in memory. And so the difficult part, as I said, is that different elements shared some points. So the memory accesses are not that good. So we have to do gathers, and so to put back results into memory, we have to do scatters too. So let me. So how the vectorization is done? So the idea is simple. So we vectorize, on the element. So each thread, each lane, I should say. So each lane of a SIMD vector will treat one element. And this slide is about 256 bits SIMD vector. So this works was in fact done on Intel and with AVX, AVX2, and AVX 512. And so this was published at WPMVP. And so the current work that I'm presenting you today, so is about the same work, but on Neon and SVE. So the differences between Neon and SVE when programming is that in Neon you can as the vector size is known at compile time, you can write arrays of SIMD vectors. You can, and also this is a C extension, C++ extension to the language. You have the overload of some operators like bracket. You can access a lane directly. And you can, of course, add and multiply SIMD vectors together. And so this does what you think it does. But for SV, this is not the case. So first, when you I will say when you write a pure SV, so you suppose that you don't know the vector length at compile time. And so you have to replace, declarations. So basically, as you can see, so when you have for the local array, so what we do is we declare an array of SIMD vectors for Neon, but for SV, we have to go back to, let's say, a basic float and to do an array with this SV intrinsics, which gives us the number of floats inside SV vector. And so we have to work with that. And so another drawback of this is that, to get data and to put back data into this local array, we have to do explicit loads and explicit stores, which is not the case in the Neon version, because as the array is known at compile time, you don't have to write explicit load and stores. Also, writing SV is really hard because there is no operator overloading. You have to load, store, explicit. As I said, you have to write explicit loads and store, which makes the code very verbose and very hard to write, read, and maintain. So here what we got. So we compiled our kernel with GCC and ARM on the Thunder X2 and Graviton. And so we have basically a speed up of 2, basically, on the Thunder X2. But on the Graviton, we do not have such a speed up. And when we took the binary from the Thunder X2 and we execute them on the Graviton, we got, as you can see, the yellow bars, which indicates that it seems to, yes, that the Graviton microarchitecture seems to be better than the Thunder X2. So this is under investigation, so we do not have all the answers, and we are still investigating this phenomenon. And so I forgot to say the kernel is memory bound, because in theory we would expect to have a speed up of 4 because we can put 4 floats inside a Neon SIMD vector, but we have only a speed up of 2.3 to be exact. Then we did some experiments for SV. So we did not have access to a real SV machine, so which is sad, because all I have to present to you is a result, from ARM IE, so the emulator. So what we can see is that we have a good vectorization ratio, about 70%, and that it scales well. So the more we increase the SIMD vector size, so the less instruction we have. So in conclusion, so we have a significant speed up limited by memory. And so we hope that we will have a better speed up on a real SV machine due to HBM. And so, as I said, we have some difficulties to write explicit intrinsic code. So what we will do now is porting the mini app to NSIMD. So NSIMD is a vectorization library, so that a lot of the verbosity that I talked about operator overloading, stores loads will disappear with the NSIMD. So we hope that we will be able to test on the A64FX We have also ideas about memory layout optimizations, and we want, of course, to integrate the kernel back to FESpec, to do a full bench with MPI and so on. Because all this work is a work on a single node, on a single core. So a quick overview of NCMD. So we support, of course, Intel Intrinsics, ARM Intrinsics. It's on GitHub. It's MIT license, and so so far we have the same performances as explicit intrinsic written by hand, and we have also put NCMD inside GROMACS to have SVE support. So that's 10 minutes. So I stop here. Thank you very much.
Thank you very much. Let me see, do we have any questions? I haven't seen anything come yet.
I've got a question, actually.
Go on, yeah.
So GCC supports an MSVE vector bits flag to enable vector length specific optimizations at compile time. I'm wondering how, or do you think your results would change, or how would this work change if you could assert a specific SVE vector width?
So so if we know the vector at compile time, basically we go back to the neon stuff. I mean, it's like traditional SIMD programming, but the experience from GCC on Intel well says that even if we know the SV vector size at compile time, I don't think it will give much more performances. I mean, it will be the same basically. So no auto vectorization basically.
Interesting. Thanks.